all of this started with a book that I wrote 12 years ago, which is called Cells, Gels, and the Engines of Life. And that book dealt with biology. It dealt with the role of water in biology. And the main point, the main theme of that book was that if you don't understand the role of water in biology, you won't understand biology. And most attempts at understanding biology relegate water to a very secondary kind of role, very unimportant. Water is essentially the carrier of the most important molecules of life, like proteins and DNA. The proteins do most of the work, and the water just sits there to suspend the proteins and not much more. The book challenges that view and presents evidence that water is absolutely central to everything that the cell does. So, and out of that came the idea that the water that was sitting inside your cells and my cells is not like water in a glass. It's actually ordered next to surfaces. So it's something like this. If you have a protein, which your cells are full of, usually the charged regions of the protein are on the surface of the protein and the water is right next to it. So what happens? Well, what happens is that the protein tends to order the water molecules out to some level. And it was really difficult to figure out how far this ordering occurs. Now, the biology textbooks will tell you that there may be 1 or 2 or 3 ordered layers, not more. And the book suggested that there might be dozens, if not even up to hundreds of layers. And we're interested in finding out much more about this kind of ordered water and what it was like and such. And the one clue that we had was that this acts pretty much like a crystal because it's ordered, just like, for example, ice. And ice excludes particles and solutes as it forms to form the very regular crystalline structure. So we knew that was the case. And we came upon that through the courtesy of a Japanese investigator. We came upon a neat method to figure out the properties of this water and how far out it actually extended. And that's shown here. And it's very simple. The hydrophilic surface is that of a gel. So here's the edge of the gel. We put the gel in a chamber. And then we dumped in a suspension of water and particles. And the particles that we used are microspheres. And they are just what they say, little spheres, micro-sized, typically 1 micrometer in diameter. And you can buy them. They're very readily available. And the idea was this, that if there's some kind of ordered water, and the ordered water tended to exclude these particles, by measuring the zone of exclusion, we can tell how many particles, how many water molecules were ordered. This was not definitive, but it gave us some idea of what might be happening. So we did the experiment, and what happened, what we saw, is that right after we put the suspension in, the particles were expelled progressively from this area. And the video stops here. If you look in the microscope, you'd see these particles dancing around in Brownian motion, but they would never enter back into this region. So this region looked like conceivably might be the extent of the ordered water region. And it was pretty large. We're talking 50 or 60 micrometers, which is substantial. So we call it the exclusion zone because it excludes particles, I'll show you later, solutes, or EZ, which is sort of easy to remember. So another example of almost the same, just to reinforce, is a piece of Naphion. Naphion is a polymer, has a backbone just like Teflon. It has a lot of charge groups, sulfonate groups, which makes it charged. So you take a piece of Naphion, you cut, it's a sheet. So you cut the sheet as you like, lay it down on the bottom of the chamber, and add the suspension of microspheres in water and see what happens. And what happens is pretty much the same as I showed you in the previous slide. The exclusion zone builds, and it keeps building, and I've stopped it prematurely here. It actually built somewhat to maybe 400 micrometers, 300, 500, an enormous distance by molecular standards that you can see even without the microscope that we use here. So by now, this finding has been confirmed in many laboratories, and in fact, we discovered that it was published in 1970 by a group, almost the same experiment. We hadn't known about it, same results. So the first issue is generality. These exclusion zones, are they general, or is it just these couple of examples here? And we spent quite a few years testing, and just to summarize, the surfaces that create these zones are many kinds of gels, many kinds of polymers, charged especially, hydrophilic polymers, biological surfaces of various sorts, and even single molecular layers on gold, self-assembled monolayers. That is, one molecular layer seems to be enough. It's like a template, enough to create whatever happens in this zone. What's excluded from it? We found essentially everything down to at least molecular weight 100 and even lower. Okay, 100 is clear and lower is iffy, but I think it's true. And just an example of small molecular weight substances that are excluded is shown here. So at the bottom, we have a piece of Nafion put in a chamber, and all we've done is add water and pH-sensitive dye. Now the pH-sensitive dye, just like litmus paper, it changes color depending on pH. So the main point here, though, is that these dyes, it's a mixture of 4 or 5 different dyes of molecular weight, roughly 100 or so, and they're excluded from this region because you can see this region is clear, has no dye in it. You can see it better on my computer, but it's there. So that's an example of the kind of exclusion. More important, I think, is the pH value. So this has the orange color corresponds to a pH of 3 or less. That's very acidic. It means it's just full of protons, positively charged protons. We've actually measured in some cases using a different kind of probe, pH 1. This is extremely full of, full of protons. So to summarize, I just wanted to summarize the first issue that almost everything is excluded. Now the next question is whether this zone really is physically different from bulk water. And I've suggested that it might be, that that's what's responsible for the exclusion, but I haven't really shown you any evidence. Now, what I'd like to do is to provide the evidence. I'm not going to do it in detail, except for one finding. Most of it's been published, and it's also in the book that is sitting out there. Just quickly summarize, and I'll show you one example of one of those pieces of evidence. The first is that the water molecules inside this exclusion zone are more constrained than bulk water, and the technique we used. And the molecules are more stable than bulk water. We found that this is not neutral. The molecules actually inside the exclusion zone are negatively charged, typically. We found that they also absorb light. They absorb light very much at 270 nanometers. That's in the UV region. Bulk water doesn't. It's more viscous than bulk water. The molecules inside the exclusion zone are aligned, and we measured birefringence. We used birefringence to show that. And the molecular structure appears to be different based on the infrared absorption. I'll go into that in a moment, different from bulk water. And optical properties differ also. The two Russian groups measured the refractive index of the exclusion zone water compared to bulk water, and it was about 10% higher. Both groups found the same. So I just want to briefly go through the negative charge because that's really important for what follows. And the experiment that we did to check it was we put a gel next to water. So inside means the inside of a gel. This is a polyacrylic acid gel. And we put it next to water. So outside the gel, inside the gel. And we used 2 electrodes to measure the potential difference. These are microelectrodes, the ones that taper to less than 1 micrometer. So we have good spatial resolution. So you put one microelectrode out here as the reference, and the other one is the probe electrode, and you move it from point to point. So you can see it starts here at this distance from the interface. And at this point, the potential difference between this point and the reference is 0, which is good. That's what you expect. Nothing to change, no reason to find something different. And as you advance the probe closer and closer, you begin to pick up a negative electrical potential. Here down to 125 or so millivolts negative. And the region of negativity corresponds roughly to the size of the exclusion zone. So it looks like the exclusion zone is negatively charged. We got rid of the gel and replaced it with a piece of Nafion, did the same experiment. Results are here. It's pretty much the same except quantitatively you can see it differs, that the region of negativity begins quite far and becomes substantially negative roughly around here and gets more negative. And Nafion's exclusion zone is correspondingly bigger. So it looks like it looks like from these measurements that the exclusion zone is negatively charged. So it's a little odd that it's negatively charged because remember, we started with water. Water's neutral. So how do you start with something that's neutral and you wind up with something that's negatively charged? You can't just invent the charge, pull the charges out of a hat. So an idea is that, well, maybe the water molecules are somehow splitting into negative and positive regions, and we're measuring the negative one, and therefore a positive one should exist somewhere out there. And the question is whether it really does exist. Can you identify it? Well, I've shown you from previous measurements that it does exist. So here's a slide that you saw earlier. I just turned it 90 degrees. Here's the exclusion zone, which I just showed you is negatively charged. And remember, this red color corresponds to a very low pH, lots of positively charged protons. So indeed, we have negative and positive, and it looks like basically that the water is being split somehow into a negative and positive components. So we have a charged battery in water next to a hydrophilic surface. So back to this list, if you want to find out more about what this EZ structure is, you look at a few of these characteristics that we've measured. The molecules are aligned, they're relatively stable and constrained, and so what does this correspond to? And I think the best description is it's some kind of liquid crystal. It doesn't tell you exactly what or what kind, but something like that. So what I've shown you so far is summarized here, that you have a hydrophilic surface next to water. We've known for a long time that at least a few molecules of molecular layers are ordered, but what we found now is that, first of all, it's something like a liquid crystal, which sort of fits this in a way. It has negative charge, which doesn't fit because these are dipoles. Dipoles are neutral. You can stack an infinite number of dipoles and never get a net negative charge. We have a net negative charge, so unfortunately, this says something about this model. It doesn't work. This region excludes solutes profoundly. I've shown you evidence for that. And as I just suggested to you, it's not a dipolar region, but something else. It may extend very far. The textbook says a few layers. If what I've shown you is correct, it's a few million molecular layers, depending on the surface that we use. And the suggestion from all of the evidence that I just summarized, I haven't presented it, is that it's different from ordinary water. And it was suggested 100 years ago by a prominent physical chemist that water really doesn't have 3 phases, the solid, liquid, and vapor. It has 4 phases. There's some interfacial phase. And this idea of a 4th phase has sort of gone in and out of favor over the past century. Mostly it's been forgotten. And everybody learns that water has 3 phases. And it's possible that what I've shown you here is evidence for a 4th phase, a distinct phase. It's bounded, it's a different structure, and there's a lot of it. I think the structure is actually a sheet-like hexagonal structure that looks like this, which resembles ice in a way, but it's not exactly ice. And I didn't want to take the time to go through it because many of you saw it from yesterday in previous lectures, and it's in the book. And I don't want to go into the rationale for it, but I can just say that there's a considerable amount of evidence that suggests that instead of dipoles, this is a sheet-like structure built out of water next to these hydrophilic surfaces, and so they build something like this. And this structure, if you look at it, just take one plane, it looks something like this. And the ice structure, those of you who know it, consists of hexagonal sheets stacked up on one another. This is kind of like it, but the sheets are actually out of phase, shifted relative to one another. So it's not exactly ice. It's different, but it's ice-like. And if you count in these sheets, if you count the numbers of oxygens and hydrogens are here, you might think, well, you know, water is 2 to 1 to H2O. This is not H2O. Actually, it's H3O2. So it's not water. This thing has, if this is correct, the water has undergone a chemical change to a new species that looks like H3O2, not H2O. So the answer to question number 2 is the EZ physically distinct from the bulk, and I think the answer is yes. I've shown you evidence, and the best evidence we have is that it's a layered honeycomb kind of structure. Okay, Now, next question is, if we have a battery, the exclusion zone is negative, the next region is positive. What charges the battery? You can't get something for nothing. And so it's like your cell phone battery, you need to plug it in periodically to recharge it, otherwise you're out of luck. So what charges this water battery? And it took us a few years before we finally got a hint of what might do, and it turns out it's light. And thank you, Don, for the introduction about light. Incident. And how did we find out? Well, we started with a casual experiment by an undergraduate working in the lab who walked by. We had a preparation here showing the microspheres and the exclusion zone. He brought over a lamp and shined the lamp on it. And what happened was that, so here's the exclusion zone. This is a piece of Naphion, exclusion zone, microspheres. And when he came over with the lamp, the exclusion zone expanded. And when we took away the lamp, the exclusion zone came back to its normal size. So from these experiments, we did many experiments, and we published several papers. And basically what we found is that all wavelengths of light from UV to infrared through the visible were effective, but by far the most effective was infrared. Infrared wavelengths, for reasons that are not clear, you'd expect that UV would have higher energy, but infrared was really powerful in growing this exclusion zone. We could use weak infrared sources, weak enough that the temperature of the chamber would never increase by more than 1 degree, and we could, if it was on long enough, the exclusion zone could build to 10 times the original size. So infrared, well, infrared is typically associated with heat. That's the most familiar manifestation, but actually infrared is all over the place. It comes from the chairs and the rug and you and me. And if we were to turn off all of these terrible lights and do the experiment, growing an exclusion zone, we get pretty much the same result as if all the lights were turned on, because there's an infrared coming from everywhere. If I were to use an infrared camera without these lights, I'd get a perfect image of all of you. So infrared is literally free energy that we get. This is the energy, this free energy is what's used to build exclusion zones. So you have a situation like this. You have a material and easy water, and you add more infrared, or just the infrared that's around, and it grows the exclusion zone. And okay, so the answer to question number 3 about the energy, this was a quick summary of a lot of results, is that the exclusion zone buildup is powered by photonic energy, which orders the water and basically charges the water battery. So the situation is sort of something like this. And if you think about it, it seems exotic: light, water, etc. Light giving energy. On the other hand, if you think about the plant, what plants do exactly that. They take the energy, electromagnetic energy from the environment, and they use it. They convert it into chemical energy, which does all kinds of work, metabolic work and growth, bending, what have you. And I'm suggesting that the same thing occurs in water. It's not a surprise, because plants are made mostly of water. So this glass of water contains energy, and that's why I use this familiar equation, almost familiar. You guys are mostly Einsteinian, so an equation similar to this is one that you know quite well. But what I meant is, even though the units don't match, that it's hard to separate energy from water. Okay, so now what about biology and health? I want to move to that. And what's new? How does this water stuff somehow relate, or possibly relate, to health? And I'm going to present to you a potpourri of different ideas, which may seem somewhat unlinked to one another, and a lot of it is speculative. But I want to suggest to you that the water and light play a very critical role in your health. Okay, first thing is, we receive infrared energy all the time, and also visible light and such. And the question is whether just like plants, whether we can use this energy for anything useful, or do we simply absorb it and re-radiate it without making any use of it. Well, last night I presented evidence that you could put a tube in water, a hydrophilic tube, and get flow, perpetual flow through the tube that was mediated by the absorption of light. So water really does act as a transducer. It converts electromagnetic energy into mechanical energy of flow. But so we receive this energy, and just like plants, the question is whether we do pretty much the same thing that plants do. In other words, do we sort of photosynthesize? Now, I'm not suggesting that we photosynthesize, but I'm suggesting to you that we might use light in some ways. Of course, photosynthesis involves many different steps, some of which are not known. The first step in photosynthesis is to take the light next to a hydrophilic substance, a chromophore, and split the water into positive and negative. That's exactly what we're talking about here. So you know, if you were nature, Mother Nature, and you progressed from plants to animals, would you just simply drop a process as successful as photosynthesis, or at least the first step or two of photosynthesis, or would you keep it as maybe a backup measure, or even more than a backup measure? So I'm suggesting that that actually may be possible, that you're using this energy. Now, if that's true, the question arises, well, gee, you know, if we're getting energy from water, can we avoid eating? Sounds preposterous. But some of you know that there are people called breatharians who essentially don't eat. They basically just drink. And actually, one example, someone in a humid environment who actually doesn't even drink and doesn't eat. Now, I'll just show you about this guy because I happen to know very well about this fellow. Some of you will know Prahalad reported he grew up in a cave somewhere in India, and he claims that he was approached at age 7 or 8 by angels, and the angels told him that he didn't need to eat or drink, in fact. And after 65 years, he reported himself to the local government and said, I haven't eaten or drunk anything for 65 years, and you guys ought to know it. So obviously it sounds like this is the biggest malarkey that you ever heard of. However, I think it's not. And the reason I think it's not is that I came into contact with the physician who led a group of 15 physicians who examined this guy, put him in the hotel room, or in the hospital room, for 2 weeks. And the place was sealed, filled with video cameras, and filled with physicians ranging from urologists to pulmonologists to psychologists or whatever. And they examined this guy not for 65 years, but for 2 weeks. And they certified that this guy didn't eat or drink anything for 2 weeks, and he was just fine. They made numerous physiological measurements, which were reported at a water meeting that we conduct annually. And I must say, this was absolutely convincing. And the physician in charge told me that this guy, when he was finished in a couple of weeks, he could run up the stairs faster than the physician who examined him. So I think it is possible. Now, a lot of people, a sizable number of people can really get on without eating. And a few books have been written and lots of discussions. Just in Seattle, where I come from, just in the past 2 weeks, a woman finished fasting for, I think, 45 days or something like this, and feels just fine after that. She decided to go back to eating. All she did was drink. And so these people, almost to the last person who do it, claim that they somehow get their energy from light. Now, we talked a lot about light and how light hitting the water separates charge, creates potential energy, builds easy water, which fills your cells. So there's a possibility that the energy that we're getting and the ability to accomplish seemingly miraculous feats like this may come from light that's around us. Light really sustains us. And one of the books that was written by a fellow who's done this, it's called Life from Light. So now I'd like to turn to another issue. I said this would be a potpourri of issues. and that maybe it's a little bit disorganized, but I want to talk about ultra low friction. So the question is, how come your joints don't squeak, right? So when I do this, my joints, sometimes they squeak a little, but they don't squeak. Now, so how does biology accomplish this miraculous feat? Well, you know, when you talk about friction, you're really talking about asperities. So if you shear two surfaces by one another, the bumps tend to collide with one another, and the result of that is that you get friction. So if you can avoid those bumps, you can reduce the friction. So you can see that in the case of the mountain peaks, if you had somewhere were able to separate them, then they'd shear by one another with no problem, and friction would diminish. So if you have two surfaces that have some roughness, every surface has roughness, if you could somehow separate them. So for example, if this is a hydrophilic material and a hydrophilic material, and you put water in between, well, most of us would say, well, sure, you put water in between, you get lower friction, but I think it's more than that. I think it's that if these are hydrophilic materials, you get an exclusion zone here, you get an exclusion zone here, and as I mentioned to you, you get lots of protons here, huge numbers of protons. Now, these protons repel each other. Because they repel each other, they push the surfaces apart. And I think this is the principle of low friction. I think it also operates on the surface of ice, something similar to this. So if you look at a joint, this is a typical joint. You have a bone here and a bone here, and a ligament connecting these two. And the bones don't rub on each other. They have an interesting structure. It's called the joint capsule. And what it does is this region here is lined with cartilage. And cartilage is nothing more than a gel, and cartilage is right here. And so because this is a gel, and this is a gel, you should have an exclusion zone here, an exclusion zone here, and it should be filled with protons. And those protons can't escape because you have this capsule keeping them in. So the situation here may look something like this. Here's cartilage corresponding to these green ones. And in between, you have these protons that I talked about, and these protons will keep the two bones apart from one another. And people who investigate joints like this claim that no matter how much load you put on the bones, they don't touch it. The cartilage surfaces don't actually touch one another. Nobody can understand why. And I think this may be the reason. So I think this is the reason why we actually have low friction in our joints. It has to do with those protons. Okay, now what about pathology of those joints? So, for example, you sprain your ankle. I don't know how many of you have had this experience or break. You look at your ankle, it swells, but it takes seconds. It's not a long-term process. It's practically immediate, and maybe you never asked yourself, why does it swell so quickly? It does something like this if you sprain your ankle. And if you think about the structures that are inside your ankle, besides bones and such, all of the muscles and connective tissues, I'll just give you an example of why I think this happens. So if you look at muscles, so this is an electron micrograph, scanning electron micrograph of muscle. We studied muscles for many years. And these are called myofibrils, and they run along one another. These little fuzzy ball-like structures are mitochondria. And the point I want to illustrate here is that this myofibril is connected to this one, which is connected to this one, and so on. So they can't expand laterally very much. There's a limit, the elastic limit. Now, if you look, the same principle applies if you look inside one of these. And this is a micrograph showing the protein filaments that are inside. Now, these are so-called thick filaments here. And the thin filaments are actually pulled out because this is a stretched muscle. And you see a few interesting things, the most prominent of which are these interconnections between here. These are known as cross bridges between thick filaments. They're ladder-like structures that you can see that run from here to here. So what does that mean? Well, conventional point of view is that these are actually used in force generation, and they may be. But in terms of the ability of this lattice to expand, they put constraints on the expansion because you have to pull on these cross links and they can expand just so much. So this keeps your tissue from expanding very much in the face of forces that might want to expand it, like EZs building next to these protein surfaces. So the crosslinks restrain EZ buildup, and I'll just show it more clearly here. So here's one of those thick filaments, here's another one, and these are the crosslinks. So you can imagine next to these protein filaments, you have EZ layer here and another one, and they start building up from each of these filaments, and they build and build and build, and they're going to try to build to 1 million layers and really stretch things out, but they can't because these links constrain the separation between the filaments. However, if you have an injury, you get rid of them, they break, some shear, you sprain your ankle, then when that happens, there's no restraint to swelling. And so EZ layers now can build up essentially as much as they like. And if they do, which I think they do, this is what happens. And I think that's the reason why when you sprain your ankle, why it swells in the matter of just a few seconds. And I think also the principle is similar for gels and polymers that swell, but we won't go into that. Okay, now next, what about the role of the exclusion zone in the health or behavior of cells? So cells are full of proteins. Around each protein are EZ layers, so cells are basically full of EZ water. And this actually underestimates what the packing that you see inside the cell. I'll show you in a moment. Because of tight packing of these proteins, they're actually right next to each other practically. Most of the water inside is EZ water. It's almost all interfacial water. And the cell, because it's almost all this negatively charged EZ water, the cell is negatively charged. You know, this is not rocket science. So if you look inside the cell to see what the structure is really like, according to the famous drawings, renderings from electron micrographs, you can see that it's really tightly packed. This is a 10 nanometer scale here. In fact, the average surface-to-surface distance between macromolecules is 7 water molecules. That's how tightly packed it all is. And so if it's basically all interfacial water, then most of the cell water is EZ water, and which we've known previously, but it just emphasizes the fact. Now, if most of the water is EZ water, and EZ water is negatively charged, then the cell is full of basically has a negative electrical potential. And it's been known for 70 years now that if you stick an electrode into a cell, you get negative electrical potential, 100 millivolts, 90 millivolts, something like this. And I think the reason is very simple. It's just that the water is negatively charged. Those of you who know biology and who read a biology book, the mechanism that's suggested is very complicated. It has to do with the membrane. It has to do with pumps and channels and what have you. And oddly, people have not taken into account the fact that if you stick the same electrode into a gel made of polymers or proteins, no membrane, but the same electrical potential, pretty much. So the idea that is pervasive throughout all of biology, that the electrical behavior of the cell has something to do with the membrane, I think the evidence is against that. Now, this is a cell that's just sitting there and not doing anything. But cells do things, like, for example, a muscle cell contracts. Mostly it's just relaxed, but it does stuff. A secretory cell secretes. A nerve cell conducts signals along its length, so-called action potential. And I showed in this book that these kinds of actions involve water as a central player, that it's a phase transition, that the EZ water that mostly fills the cell converts to bulk water transiently. And that's what precipitates the action. That's what, for example, precipitates the muscle contraction. Now, when that happens, of course, bulk water is neutral. So you go from negative electrical potential to 0 electrical potential. And then the restoration back to the original state, you go back to the negative electrical potential. So just shown diagrammatically, what I'm trying to say is that when you have action, when the cell goes to work and does what it's designed to do, then electrically, what happens is you go from, say, nominally 100 millivolts. This is because of the EZ water is negative. When the cell acts, the EZ water converts to bulk water, and you get roughly 0. And then it restores, and you go back to EZ. So this applies to any cell, whether it's a muscle cell that contracts, a nerve cell that conducts, or a secretory cell, what have you. The same principle applies. So this is called the action potential. I didn't give it the name, but it's known now for, I think, 70 or 80 years. And it's the same thing that happens along your nerve. So when the nerve conducts a signal, you get an action potential. That is, the water converts from the EZ to bulk back to EZ transiently. Now, I want to turn to anesthetics, because all of you who have had surgery know that, or pain, whatever, that anesthetics eliminate sensation. And it does it, at least in part, by wiping out the action potential. So if the nerves can't signal anymore, you don't feel the pain, or your brain's not working, and so you go to sleep, and you wake up in the next few hours, and your surgery is all done. I started my career as a bioengineer in the Department of Anesthesiology, and I can tell you that nobody understands how anesthetics work. There are all kinds of theories, but their act is not together, and they're still trying to figure out how anesthetics work. And I think we've figured it out. I think if you follow the logic, we know that anesthetics will get rid of the action potentials, and if the action potentials depend on the exclusion zone, this negative potential inside. If you don't have that, you can't get this phasic change of potential. So the hypothesis then is, well, if that's true, if you have an exclusion zone, the anesthetic should wipe out the exclusion zone, and that will explain why you don't get any action potentials anymore. So we tested it. We used we took a typical chamber where we measure exclusion zone with microspheres and such, and we applied local anesthetics. Two common ones. One is bupivacaine, and the other is lidocaine. And you can see that as you increase the dose, the exclusion zone goes from a normal size down to a much smaller size. This is reversible, and the concentrations used here are similar to clinical concentrations. So they both show pretty much the same result. And then we decided to try also a general anesthetic, the one that's commonly used now, isoflurane, and we get pretty much the same result, except we had this little pip here at extremely low concentrations. Well, it turns out that it's well known among anesthesiologists that if you have a very low dose of anesthetics, it's an excitatory state, not a depressive state. And in fact, when you get an anesthetic, as the concentration builds up, you go through this excited state before you go through the anesthetic state. So these results suggest that the mechanism of anesthesia, that the anesthetics act by exerting some effect on the water. Now again, this seems a radical hypothesis. However, none other than Linus Pauling, many years ago, suggested the same. He said, the noble gases, xenon, argon, whatever, they're anesthetics, but they don't interact with anything except water. They form clathrates with water. He said, I think that the mechanism of anesthesia involves water. And I think he was right. Okay, now what about pathologies and sickness? Question is, well, what is a pathology to start with? And what do we mean by pathology or sick cells? Well, if you have a healthy cell, as I tried to elaborate, you have the proteins, and the proteins are very crowded. They're working just fine, and around each protein is EZ water. And the cells are full of EZ water, so the cell has a good, healthy, negative potential. I wish it were positive, because I hate that we're called negative, but it's okay. Terminology. That's a healthy cell. Now, what about a pathological cell? Well, in a pathological cell, the proteins are not functioning. But the proteins, it's not just protein. Around every protein is EZ water. So really, it's a problem with the protein and the water, or the protein and or the water. And the cell is not functioning well because the proteins are not able to do what they normally do to perform some kind of action. So there's something wrong with the proteins, but also the cells have less EZ water, and pathological cells don't have minus 100 millivolts. They may be minus 60 or minus 50 or whatever. Those are sick cells. They're barely functioning. We experimented with them for many years earlier in my career. Now, so to kind of check this idea, we decided let's look at the substance that reverses problems that we have. And the first one that comes to mind is aspirin. So, whatever bothers you, whether it's a headache or inflammation or what have you, you take aspirin, and aspirin seems to reduces fever. It seems to help a lot. Now, why does it help a lot? Well, nobody knows exactly why it helps a lot, but I would suggest that the hypothesis is that, well, it repairs this, it brings this back to its pristine state by building EZ, right, and doing that. So we did experiments with aspirin. And since aspirin reverses various maladies, and the question is whether it really does build EZs. And unfortunately, I don't have the final results, but these are representative results. This experiment was carried out by an extremely talented high school student with supervision. So here's the control. This is a surface, and here are the microspheres, and the exclusion zone is 300. And this is just one example, and she has many. Sometimes the exclusion zone in the presence of low concentrations of aspirin will build to up to 5 times the size as in the control case. So the data are now being processed and written up, so I don't have the final result, but it's clear that aspirin builds EZs. So we conclude that aspirin and anesthetics do what we might expect them to do, and it confirms the central role of exclusion zones in cell function. Okay, next topic. I have 2 more, I think, quick ones. Is your body neutral or charged? I don't know if you ever thought about that. And most of us are pretty sure that our bodies are neutral, right?
No.
No. What do you think? I can't see who you are, but I'm glad to hear that you're...
I'm hiding in the back.
Okay, and what do you think the charge is?
I think it might be negative.
I think you're right. Okay. But now if you were to get up in front of a group and say, I think your body is negative, you might not be too popular. But just look at the arithmetic.
I never hide in the front.
Okay, so you're roughly 60% of the volume of your body are cells. Okay, and the cells are negative. Everybody knows that. Now the extracellular space, depending on where you look, maybe 20% or so of your space. And the extracellular space consists of collagen, elastin, various negatively charged proteins which attract a lot of EZ water, which is negatively charged. So we're totally now like 80% of your body is built of negative charges. So we start building up. Now what about the positive charges? Well, the spaces with the protons, the first one you think of is urine, because urine has a low pH. So you pee and you get rid of positive charges. You get rid of, when you sweat, the sweat has low pH, so you get rid of positive charges. When you breathe out carbon dioxide and water, carbonic acid, full of protons, so you breathe out positive charges. So out of this, this simple arithmetic, it looks like we're negatively charged, we're not neutral. And so a hypothesis, a simple hypothesis, that the body strives for the highest negativity. You are negative, you're not neutral, I would propose. Now, this came out of arithmetic, but if you think of the plant kingdom, you think of that plants are connected to the earth, and we know the earth is negatively charged, is not neutral. So if you have something that's stuck into something negative, it's likely to be negative. And indeed, you just add up all the cells in the plants, and you come to the same conclusion, that it too is negative. So I think that maintaining negativity is a... that doesn't look right. I think psychologists will not like this. But I think that maintaining electrical negativity is a fundamental attribute of life. which leads to, if this is true, this is sort of new principle that, I think it's true. It's something that we've not appreciated or recognized before, which leads to the idea of antioxidants. Now, you all heard of antioxidants, and the physicians and alternative medical people are saying, well, you should take antioxidants all the time because it keeps you healthy. There are a dozen different mechanisms put forth as to why they keep you healthy, and each one is mutually exclusive with the others. So, we look for a simple general mechanism, and if you think about it, I think it's simple. So remember basic chemistry, reduction is a gain of electrons, and oxidation is the loss of electrons, right? And so we're talking about oxidation, oxidants here, loss of electrons. So antioxidants, should prevent the loss of electrons, right? And therefore, if you prevent the loss, it maintains negativity, and therefore it should promote health, because health, I think, is equivalent to maintaining that negativity. By the way, it's well known, some of you know, that if you expose yourself to negative charges in the environment, you feel good and you get healthy, and positive ions is the opposite. That's well known. Now, what about water? Returning to, this is the sort of last few minutes of health benefits from drinking water. Is that possible, or is that nonsense? About 25 years ago, a book appeared. It's called, as you can see, Your Body's Cries for Water. You're not sick, you're thirsty. Okay, this is written by a physician, a prominent physician from Iran. And he got the idea that water was critical for your health. So a patient would come to him with this complaint or that complaint, and he said the same thing that your grandmother said: drink more water. And he reports in this book that this is like a cure-all. Just drink a lot of water and you'll remain healthy. So his point of view is that we're missing, our cells are missing adequate water, adequate hydration, and we need to replace it. So he said, just drink more water. But I think that some kinds of water are better than other kinds of water. So if we look inside water, water is the ultimate solvent. And so you have a particle or a solute or something, and you have EZ water surrounding it, and then you have these protons. And one of the interesting features is that when you have minus and plus, you have a high dipole moment, right? And that's characteristic. If you have EZ water, you have these dipole moments. And so if you think about it, so the cells are full of EZ water, and the cells are negative. And the cells that are sick are also negative. They're just slightly less negative. Then think about drinking EZ water. Well, first, if you drink regular water without EZ, ultimately those cells will rehydrate as they need to. But if you drink EZ water, remember, EZ water has big dipole moments because it's got lots of separated charges. So what happens is that those dipoles orient the right way, plus on this side, close to the negative cell, and get drawn in very quickly. And I think that's why EZ water rehydrates cells very effectively. And I'm not going to tell you about all the evidence, but people come to me because we run these water meetings annually. And various people have produced various kinds of water, and they have vast evidence, although not the double-blind clinical studies that we've all come to accept, but very impressive evidence that water not only can improve of various types, can improve your health, but actually that they can reverse pathologies. And I'm happy to talk with you afterward in details. We would like very soon to do objective tests on these waters to really see which ones are the best and which ones improve health. And also, if you think about drinking EZ water, right, you have separated plus and minus. That's potential energy. Now, if you swallow potential energy doesn't vanish. So what does it do? Well, again, you could just radiate it out, or it's possible that that the water contains energy, no calories, but lots of energy. And so you can remember the times when you've gone through some athletics and you're sweaty and tired, and you drink a few glasses of water, and suddenly you feel energized again. It could be psychological, but you really have to ask how much energy actually comes from the potential energy that's contained in the water, perhaps more than you think. Okay, so the main conclusions here are I think there are two or three. The first one is I wanted to emphasize the fact that water is it's not just a solid, liquid, and vapor. We've identified what we believe to be another phase of water. It's distinctly different from this one and distinctly different from this one. Oh, it has some features of both of these. In fact, the molecular structure is kind of close to that. And I haven't told you this, but in the book, you will find that in order to go from water to ice, in order to freeze, it's obligatory to go through this phase and this phase. And if you melt the ice, it's obligatory to go through this phase before you get to this phase. And the evidence is in the book. So water has 4 phases, I think not 3 phases. And water is getting energy from the environment all the time. Water is not just sitting there in equilibrium with the environment. It's actually an engine of sorts. It's taking in energy from outside and transducing that energy into other kinds of energy, 1 or 2 of which I just mentioned, but there are more. And I think that this water is centrally tied to your health, and maintaining this kind of water around each protein inside your cell allows those proteins to do what they normally do to perform whatever function the cell is required to do. And if this EZ water is missing for whatever reason or is reduced, then your function is not optimum. And you need to replenish it in order to build back up to optimum function. I have a fair amount of contact with some of the alternative medicine people, and more of these people are turning from probiotics and vitamins and such as the cure-all and antioxidants to water as the central entity involved in maintaining health. And I think this is a revolution that's coming in the future. So a lot of this stuff is included in the book, and there are some signed copies out there. You could also, if you choose not to buy one of these books, they're pretty cheap. You can look at ebnerandsons.com, the website for the book, and read a few chapters free of charge if you prefer to do that. So I think I'll stop here, and because I've used up all my time, and entertain some questions if you have any.